Welcome back to physics. So now we're going to start talking about some things that include Newton's laws. And the first thing we need to talk about before we get into Newton's laws is free body diagrams. Included in this PowerPoint are going to be some vocabulary words that we need to know and understand. And we'll go through those. So Newton's laws vocabulary. A force, it is simply a push or pull on an object. Pulling a rope, pushing a car that's run out of gas, a push or a pull on an object. Inertia, we've kind of talked about this, the resistance of an object to change in motion. So if an object's not moving, it doesn't want to move, and if it is moving, it wants to stay moving. So inertia is the resistance of an object to change in motion. Acceleration, we talked about this in the last unit. It's a rate of change in velocity of the motion of an object. Acceleration. Free body diagram. It is simply a diagram of all forces acting on an object drawn as vectors outward from the center. This will all make much more sense further on the PowerPoint when we draw some free body diagrams. Just write down the definition for now. It's a diagram of all the forces acting on an object. Weight. It's the gravitational force that an object exerts due to its mass. Weight and mass are not the same thing, and we'll talk about that in detail in class, and we'll talk about why. Mass is the amount of matter an object contains, or simply a measurement of its inertia. So the more mass, the more inertia. And we'll see that in a demo that we do during class. Net force. It's the sum of all force vectors into a combined or total force. So we will be determining the net force on objects using free body diagrams later on. So the net force of all force vectors in a combined or total force. Normal force. This is a force exerted perpendicular to the surface of an object that it rests on, or the support force. So if a book were sitting on a table, it's the force that keeps the book from falling through the table. And we'll demonstrate that here in the next few slides. Friction. It's a force opposing the motion caused by the interaction of surfaces. So if you've ever rubbed your hands together, you felt friction. That your hands heated up as you rubbed them together. That is the friction between your hands. Same thing if you drive a car. There's friction between your tires and the road. Otherwise, your tires would just continue to spin and get no traction, and you would go nowhere. And we'll talk about that some more as well. Torque, we're going to introduce the word here because it's part of the vocabulary, but we'll actually have a separate lecture on this later on. And it's the product of the force and the lever arm that may cause rotational motion. So it's the product of the force and the lever arm that may cause rotational motion. So free body diagrams, what are they? Free body diagrams are simply a picture that shows the size and the direction of all forces acting on an object. If you look here, it's drawn as a box generally, and then you have the arrows drawn in either direction. So always, 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 we will have the force of gravity, which is annotated by a force with a GRAV, or F sub G is fine as well. The normal force is always perpendicular to the surface. So force norm, N-O-R-M, or force of N is fine as well. We'll talk about that in class. Then you have the force applied. So if something pushes or attempts to push an object or pull an object, then there's an applied force. And then the force of friction, that is the force that opposes the motion of an object. Usually has to do with surfaces in contact, like your hands rubbing together, or your tires on the road, or sandpaper and wood. That's friction. So we'll talk about that in greater detail. So here's the steps to draw a free body diagram. First off, you may be looking at a picture that has more than one object. You're going to pick one object to analyze. We cannot do more than one. Second, you're going to draw a box to represent the object. After we draw the box to represent, then we're going to draw an arrow to represent each force acting on the object. And then we're going to make sure the arrow shows the direction and relative size of the force, and we'll talk about that. So in the first problem, here's a book at rest on a tabletop. And it says, diagram the forces acting on the book. So the first force we're always going to draw is the force of gravity. So we're going to put that in. And then the next force that we're going to draw is the normal force. So we'll put that in as well. So here's our box. We drew it. Force of gravity was acting down. The normal force is acting upwards. Therefore, the book remains at rest. So you could draw a fancy picture like they did on the left and show the arrows showing one going up and one going down. But when we draw our free body diagram, we just want to draw the box and label it this way as it is on the right hand side. If the book were moving, then we would have to draw a different free body diagram. So the forces are balanced, so they cancel each other out. So if they weren't balanced, the book must be moving, as I said previously. So here's the second problem. An egg is free falling from a nest in a tree. Neglect air resistance. Draw a free body diagram that shows the forces involved. So here's our egg. It falls out. What forces are acting upon it? So first off, we always know that the force of gravity must be acting upon it. Now, is there any other force? We said neglect air resistance, so shouldn't have anything in the upward direction. Nothing is pushing or pulling it, and there's no friction. And air resistance does have a friction. We call that drag, but we'll talk about drag later on. So if we drew that free body diagram, it would simply look like this: force of gravity, straight down because it's going down towards the earth, and it's moving in that direction, which we expect because we have unbalanced forces here. So we have unbalanced forces, so the egg will accelerate downward as we expected. The third problem here is a flying squirrel is gliding, and it says no wing flaps. If you didn't know what a flying squirrel is, Google it. You can see one. They kind of glide between trees. They don't really fly. From the tree to the ground at a constant velocity. It says consider air resistance. A free body diagram for the squirrel would look like this. So here's our squirrel. See, there he is, kind of flying, sort of, running in the air. So if we drew a free body diagram, gravity, as we said, pulls the squirrel downward. And then we say consider air resistance, so the air would push upwards. But the arrow, and it says at a constant velocity, if we go back, it said the squirrel is gliding to the ground at a constant velocity. So these forces are balanced somewhat because the air is pushing up and the gravity is pushing down, so it's not going to be accelerating one direction or the other. It's just going to be kind of floating downwards towards the ground. Now, if it said that it were accelerating towards the ground, then that arrow on the bottom would be larger than the one on the top. So when we draw our arrows for our free body diagram, they need to be representative of the amount of force each one is applying. And if they're equal and the object is not moving, they should be of the same length. Problem number 4. A rightward force is applied to a book at rest in order to move it across the desk. Consider frictional forces, neglect air resistance, construct a free body diagram. So we have the force of gravity acting downward. We have the force normal opposing it, so the book doesn't fall through the desk. It says the force applied was to the right, so we have a larger arrow to the right, and the force of friction will still oppose it, but it said we're moving to the right. So normal force and gravity cancel each other out, but the force applied will overcome the force of friction, allowing the book to move. And we'll demo this in class. Problem number 5. A skydiver is falling with a constant velocity. Consider air resistance. Draw a free body diagram for the skydiver. So he's falling at constant velocity. That's important. So gravity pulls up on the skydiver. Pulls down the skydiver while air resistance pushes up. As you can see, those forces are equal, so the skydiver is not accelerating in either direction because he has zero acceleration. So it has arrows of equal length, even though the skydiver is still moving and falling towards the earth. It's at a constant velocity, no acceleration in either direction. Let's say a gust of wind came along and pushed upward and the skydiver went back up, then we would draw that force of air longer, and it would push it in, the skydiver would accelerate upward. Similar, if all of a sudden all the air went out from underneath of the skydiver, that force of air would get smaller and he would start accelerating towards the earth. Problem number 6. A man drags a sled across a loosely packed snow with a rightward acceleration. So it tells us right here that the sled is accelerating to the right. Draw a free body diagram of the forces acting on the sled. So of course I have the force of gravity acting downward. We've talked about that. The sled doesn't fall through the ground, so I must have a normal force pushing upward, and then I'm accelerating to the right. So once again, I'm going to have a longer arrow in the direction of the force applied, but there is still friction. Even though it's snow, there is going to be some friction. Otherwise, once he got moving, he would never stop moving. He'd move extremely fast. So that friction slows his progress a little bit, and then so we have a force applied to the right. We have rightward acceleration. So same forces that you're always going to have, just different lengths of arrows depending on what we have. Problem number 7. So this is a football moving upwards towards its peak after having been booted by the punter. Neglect air resistance. Draw a free body diagram of the football in midair. So of course the ball is in the air. So long as touching the punter's foot, it's in the air. So here's our punter. He's kicked the ball. It's in the air. We want to draw a free body diagram where it's at. So in this case, the force of gravity is acting upon it, but is there anything else? So I would say not, because we didn't consider air resistance. So the ball is kicked, and if we wanted to have an applied force, we would have to draw the free body diagram right as the punter kicked it. Then there would be a force applied, and there would be also the force of friction against the shoe of the punter. But we didn't consider those things. We only considered once it was in the air, and since it's in the air, only gravity is acting upon it, and it's going to come back to the earth, as we all know if we've ever watched a football game. When the punter punts the ball, it falls back down eventually. So force of gravity would be the only force acting upon it. Problem number 8. A car runs out of gas and coasts to a stop on a flat ground. Draw a free bodygram of the forces acting on the car. So now it ran out of gas and it coasts to a stop. This is going to be confusing to a lot of you because you're going to say, well, there's a force applied, but is there? So we're going to have the same forces we always have. We're going to have a force of gravity acting downward. We're going to have a normal force acting upwards. And we're going to have just the force of friction to the left because that's what stops the car. Now, if I said that the driver was accelerating and pushing on the gas, then there would be an applied force to the right. But since we said it coasted to a stop, that lets you know that the only force acting on it is that force of friction. So you have a normal force going up, force of gravity going down, as usual, and then a force of friction to the left. No applied force to the right because the car was coasting, no engine movement. Alright, well that's going to cover everything that we need for free body diagrams. I know this is a lot of information all at once, and we'll talk about them more in class. I just wanted you to understand the basic forces that we're going to talk about. The normal force, the applied force, the force of friction, the force of gravity. Always, always, always a force of gravity. If it's on a solid object such as a desk, a table, a chair, then you're going to have a normal force opposing it, the ground. If something is pushing or pulling it, it's going to have an applied force in that direction. And if it's on a surface such as the ground or a table, then there's going to be friction opposing it. And then if we're in the air, we could consider air resistance if that is the case. So this is Mr. Havens with Free Body Diagrams. Over and out.